Hello everyone, this is Dr. Lennon, and we're going to go over the Test 2 review. The Test 2 review incorporates a lot of the basically Chapter 6 and Chapter 7. The first thing we're going to look at is finding the area between two curves. So basically we're looking to find the area between x squared plus 1 and y equals 2x plus 5. So one of those things is a quadratic, so its graph looks like a parabola, and the other thing is just a linear function. So basically the picture that we're looking at here, it looks something like, so we have our xy graph and we're graphing from 0 to 1. We've got this parabola, and then we've got some line. So something like this. Well, maybe it doesn't look quite like that. I mean, we don't necessarily know that they probably aren't going to intersect during this region, but y equals x squared plus 1 maybe looks something like this. This is probably more accurate. And then y equals 2x plus 5. So this has a y-intercept of 1. This one has a y-intercept of 5 and a slope of 2. So this line's maybe doing something like this. And then we're just trying to find the area between these two curves from 0 to 1. So basically we're looking for this area right here, this shaded region. And the way we do that is we just integrate from 0 to 1 with the curve on top minus the curve on bottom. So the area here is going to be equal to the integral from 0 to 1 of 2x plus 5 minus x squared plus 1 because the parabola is on bottom. So we get the integral from 0 to 1 of 2x plus 5 minus x squared minus 1, distributing the negative. So this is the integral from 0 to 1 of minus x squared plus 2x plus 4. So we take the antiderivative and evaluate. So this comes out to minus x cubed over 3 plus x squared plus 4x from 0 to 1. And since it's just a polynomial, the antiderivative, plugging in 0 just gives 0. So really we just need to plug in 1 here. So basically this is going to be 4 2/3, or about. So if you wanted an exact answer, 4 2/3 would be 18/3. If you were allowed to approximate, then that would be something like 4.67 if you round to 2 decimal spots. Okay, so let's go ahead and look at the next one. So I think the next one is similar, but we're going to have to find some actual limits based on points of intersection. So for problem number 2, we need to find the area between these two curves. So basically we've got a parabola opening up and a parabola opening down. So the picture is just going to be two intersecting parabolas. And because we just have the two curves, in order to find the integral, we need to actually find the limits ourselves before we can set it up. But basically the picture, you've got your y equals x squared parabola, and then you've got this other parabola that is doing something like this, and basically our shaded area is what we're looking for right there. So first, find limits of integration. So we can do that by setting the equations equal to each other. So x squared equals 4x minus x squared. We can subtract x squared on both sides to get 0 on one side of the equation and all the other terms on the other. So we get 4x minus 2x squared. And that can be solved easily by just factoring out 2x. So we get 0 equals 2x times 2 minus x. So we have our two solutions, x equals 0 or x equals 2. We can see x squared is going to be the parabola on the bottom, and the parabola opening downward has to be the one on top. So our area here is found now by integrating these two limits from 0 to 2. And we've got 4 minus x squared excuse me, 4x minus x squared. So 4x minus x squared, and then subtract the bottom parabola, which is just equation x squared. So this is the integral from 0 to 2 of 4x minus 2x squared. So again, we have a polynomial, and one of the limits is 0, so that's going to make things a bit simpler when we evaluate. So we have, let's see, 4x squared over 2, which is just going to be 2x squared. And we have minus 2x cubed over 3, just using the antiderivative rules from 0 to 2. So basically, we just have to plug in 2. So we get 2 times 2 squared minus 2 times 2 cubed over 3. So we've got 8 minus 16 thirds, which is 8 thirds. Or if you prefer a decimal approximation, that's going to come out to 2.67 if you round to the hundredth spot. So pretty similar to the first one. That's all we have to do is find those limits of integration. So let's go ahead and move on to number 3. Okay, so number 3 is a consumer surplus formula. So we've got a demand curve. So remember how the consumer surplus goes. Let's write down that formula. So our consumer surplus formula is given by, it's the integral from 0 to q of our demand function d of q minus a specific price, with q as the input variable. So remember the picture here. Basically, we've got, sorry, I've drawn this thing wrong. So we want to think about our picture as a demand function. So it's a parabola that's basically decreasing, and then we've got some price, which is here. So this downward curve is our d of q, and this horizontal line is our price, and then this shaded area where this is the value q, this is going to be our consumer surplus. So the demand function is given by that lowercase p value there, and they want to find the consumer surplus when the sales is 100. So we want to find capital P first. So capital P is going to be 2,000, and then we plug in the 100 for Q. So that's 0.1 times 100 minus 0.01 times 100 squared. So this comes out to comes out to 1890. So now we have the ingredients that we need to set up our consumer surplus for this particular problem. So the consumer surplus here is the integral from 0 to 100. The quantity that we're talking about selling of that d of q, which is 2,000 minus 0.1 q minus 0.01 q squared, and then we need to subtract the p-value that we just found, 1890 dq. So this can be simplified before we find the antiderivative. So this is going to be the integral from 0 to 100. So 2,000 minus 1890 is 110, minus 0.1 q minus 0.01 q squared dq. And so then the antiderivative, this is just a polynomial, so the antiderivative of 110 is 110q, 0.1 q is 0.1 q squared over 2, and 0.01 q cubed over 3. And that's from 0 to 100. Again, since this is a polynomial, plugging in the 0 part is just going to eliminate everything, so basically we just need to plug in 100. So we get 110 times 100 minus 0.1 times 100 squared divided by 2 minus 0.01 times 100 cubed divided by 3. And that comes out to, I'm just going to round this as a decimal, but this comes out to 7166.67. So that would be our answer there in terms of the consumer surplus. I don't know if it's specified dollars or any type of currency here, but we could assume it's dollars or something like that. Anyway, so that should be the answer for problem number 3. So let's go ahead and look at problem number 4. Okay, problem number 4 is another integration application where we're looking at the future value. So let's recall the future value formula. So the future value is given by e to the rt times the integral from 0 to t of f of t times e to the negative rt dt. So capital T is the fixed time you're investing for, lowercase t is your variable, r is your interest rate as a decimal, and f of t is your annual income stream. So for this problem, we have an annuity paying $2,000 per month. So our income stream is our first thing to figure out. So if it's $2,000 per month, it will be 12 times 2,000, which is just the constant value, $24,000 per year. So this is my annual income stream. 6.2 is the percentage I'm investing at, so that's R, 0.062, and then capital T is 6. So basically we have everything we need to plug in to figure out what this future value is. So the future value here is going to be e to the 0.062 times 6 years. We're integrating from 0 to 6. We've got the 24,000. And then we've got e to the negative 0.062 t dt. So this is our future value integral. It's we can pull all the constants out front and just figure out what those are. So the 24,000 can come out front. So we've got 24,000 e, and if you do 6 times 0.062, that comes out to 0.372. So that's e to the 0.372. And then we're just integrating from 0 to 6, e to the negative 0.062 t dt. So remember the antiderivative formula for an exponential. We just keep the same exponential, then divide by that number. So the antiderivative of e to the negative 0.062t will be e to the negative 0.062t divided by negative 0.062. So we've got essentially our antiderivative. And this one, we can't just forget about 0 because plugging in 0 into an exponential does not make it vanish. So please keep that in mind. You can pull that dividing by negative 0.062 out. It's up to you. But we essentially are almost there. Now we just need to plug things into the calculator to get our answer. So let me just plug both those values in so that if you are trying to follow along and do it on your calculator, you can make sure you're getting these things right. So we have e to the negative 0.062 times 6. So this is, and then we need to divide that quantity by negative 0.062. So we get something like negative 11.1186 minus, so minus, it's going to be a negative, so that'll become a plus. It's going to be e to the 0, which is 1, divided by negative 0.062, which will come out to be 16.1290. So then we can just plug that into our calculator. So we multiply by that result by 24,000, e to the 0.372. Sorry, I made a small mistake typing that into my calculator, so I'm just fixing that up now. But if you plug that into your calculator correctly, that should come out to 174,438.57. Was off by about 2,000, typing a wrong button. So you always have to check. Okay, so let's move on to number 5. So number 5 is solving a separable differential equation. It doesn't translate too well if I copy and paste it. So let's go ahead and just, that's xy dy dx equals y squared plus 1. So we have xy dy dx equals y squared plus 1. So separating the variables basically means via multiplication and division, we can write this equation so that we only have x's on one side and y's on the other. So basically multiply by dx to start. So we have xy dy equals x squared equals y squared plus 1 dx. So we want to move the x to the other side, so we're going to have to divide by x. And we're also going to want to move that y squared plus 1 to the other side. So we're going to have to divide by y squared plus 1 as well on both sides. So when you do that, on the left, we're just left with y over y squared plus 1 dy. And on the right-hand side, we're just left with the 1 over x dx. So now we've separated the variables, which means we can essentially integrate both sides, meaning there's only y's on the left and x's on the right. The right-hand side integrates quite easily. That's the natural log of the absolute value of x, and we'll just leave a plus c there. On the left-hand side, we're going to have to use the chain rule. So let's write that over here, integrating the left-hand side. Well, we want to let u be equal to y squared plus 1, and then du becomes 2y dy. So du divided by 2y is the same as dy. So we can change our integral to the integral of y over u times our du over 2y, and then our y's cancel out, so we just have the integral of 1/2 times 1 over u du. So this just integrates to 1/2 natural log absolute value of u plus a constant, but we already have a plus a constant on the right-hand side. So let's just replace that u by the y squared plus 1. So this is 1/2 natural log of absolute value of y squared plus 1. Again, absolute value probably on that side is unnecessary because y squared plus 1 is always going to be a positive quantity, but I'm just going to leave it alone and just write it down exactly as is. So we have 1/2 natural log absolute value of y squared plus 1. Replacing the left-hand side from that integration over here. So that's kind of like scratch work, but that's the integration by u substitution. Anyhow, so that would be your answer. Again, I don't require that you try and solve for y or anything like that. Leaving the curve once you've eliminated all the differentials, that's far enough for me. So let's go ahead and look at number 6. Okay, so for 6, we want to find the solution of the differential equation dy dx equals xy cubed that satisfies the initial condition y equals 0.25 equals 4. So that should be a point, not a colon. Things kind of copy funny for whatever reason. Whenever I cut and paste them, let's just leave it like that. Anyway, so what we want to do is we want to solve the separable differential equation the same way. So we have dy dx equals xy cubed. So again, we have dy equals xy cubed dx. And then we want to divide by y cubed on both sides. So our separable differential equation has become basically y to the negative 3 dy equals x dx. So we've separated the variables so we can integrate. Rather than writing 1 over y cubed, I've written it as y to the negative 3 because it's easier to apply the power rule. So basically we have y to the negative 2 divided by 2, and that equals x squared over 2 plus a constant. So let's rewrite this as, say, 1 over 2y squared equals x squared over 2 plus c. Now the initial condition, y of 0.25 equals 4, tells us that we can actually find the value of c by plugging in 0.25 for x and 4 for y. So let's go ahead and do that. So we get 1 over 2 times 4 squared, and that equals 0.25 squared over 2 plus c. So we have 1 over 32 on this side, and that will equal 0.25 is 1/4. So let's see, that will be, I'm getting 1 over 32 as well. So if that's the case, c comes out to 0. Let me just make sure that that looks correct. 1/4 times 1/4 is certainly 1/16 over 2. Yeah, so then this would mean c is actually equal to 0 in this case. Actually, I see that I have made a mistake here because I'm not dividing by 2 on the left-hand side. I'm actually dividing by -2. So I've left off a negative on all of these left-hand sides. So actually what happens is you end up with -2 over 32 equals c, because you have to subtract it. So we end up with -2 over 32, which is the same as -1/16. So that's the precise value of c. So for this differential equation, our solution is going to be that 1 over 2y minus 2y squared equals x squared over 2, with my answer replacing c of -1 over 16. So this would be the answer for that separable differential equation. So again, watch those negatives. They're always easy to forget about. So let's go ahead and move on to the next one. So number 7 here is, again, some of these are not so easy to write down. So what we're going to do is we're just going to, rather than copy and paste it, we're just going to write it down. So 7, we want to determine if the integral from 4 to infinity, the improper integral of 1 over x to the 3 over 2 converges, and if so, evaluate. So remember, the p-series test will tell us if you have something 1 over a power of x, if it converges or diverges. So the p-series test basically said, let's say the integral from a to infinity of 1 over x to the p. So 1, if p is less than or equal to 1, we get a divergent integral, and if p is greater than 1, then it converges. So in our problem, we have p equals to 3 over 2, which is greater than 1. So we can say that the integral from 0 to 4 of 1 over x to the 3 over 2 dx converges by the p-series test. In particular, it converges with p equal to 3 over 2, which is greater than 1. Okay, so now we want to set this up using a limit and integrate it. So let's turn this into an improper integral. Again, sorry, I put a 4 there. I meant to go from 4 to infinity. I'm trying to keep track of too many things in my head. Okay, so let's go ahead and integrate this. So we have the integral from 4 to infinity of, again, it's going to be helpful to write this just as a negative exponent when we're actually going ahead and integrating. So let's go ahead and do that. So we're going to replace that infinity with a limit as t goes to infinity. So this will be the integral from 4 to t of x to the -3 over 2 dx. So that can be integrated by adding 1 to the power and then multiplying by the reciprocal of the fraction. So this is going to be the limit as t goes to infinity of, let's say, when you add 1 to the power, you're going to get -1/2 as the exponent. So dividing by -1/2 is the same as multiplying by -2. So we get -2x to the -1/2. And we're integrating from 4 to t. So now we can plug in those results. So we get the limit as t goes to infinity of -2t to the -1/2 minus -2 times 4 to the -1/2. And remember, -1/2 just means divide by the square root. So what we end up being left with is the limit as t goes to infinity of -2 over the square root of t plus 2 divided by the square root of 4. And we can note that this limit, the denominator gets very large, so that fraction goes to 0. So we just end up with 0 plus 1. So the answer, our integral, in fact, converges to exactly 1. So again, not too difficult to tell if it converges, but we have to do a little work setting up the improper integral to determine what the conversion value actually is. Okay, 8, so we're actually going to make that the last one on this review, and we're going to stick partial derivatives just on the final exam. So they will not be on the second test, even though the review I've posted has a couple of questions involving those. But let's let f of xy equal, I believe it's the square root of y minus x, and a, we want to evaluate f of 1 comma 5, and b, find the domain and sketch a graph of the domain. So just a basic understanding of how to deal with a two-variable function. Really a pretty simple problem. A, we just plug in the numbers, so f of 1 comma 5. 5 replaces y and 1 replaces x, so we get the square root of 5 minus 1, which is the square root of 4, which comes out to 2. So basically our answer is z is equal to 2. If we want to think of that as an ordered triple, x, y, and z, if you were to graph this point, would be 1, 5, and 2. The domain, well, we're looking at the square root of y minus x, so basically that we're only looking at real valued functions in this class, so we need y minus x to be greater than or equal to 0. The input of the square root has to be a non-negative value. So basically, if we solve this, this just corresponds to y being greater than or equal to x, so that's the domain here. All ordered pairs where y is greater than x. Well, y equals x is the 45-degree line through the origin, and then y greater than x are the y values that are above it. So we just shade on this side, and that would be the graph. So any point that is shaded would be in the domain of f of xy. So let's go ahead and stop here, and that will be it. So let me know if you have any questions, and I will be sure to get those answered. So this is Dr. Lemon signing off.